Want to make a video on the fundamentals of physics. Now there's a huge amount of topics in physics, but there's basically some concepts that are the root and cause all the other phenomena. Really, the question is, what are the fundamental laws of physics, and what's the limit of our understanding, like how the world works and how the universe was formed? Like, look at this. This is pretty amazing, but this is um, this is all caused by the fundamental laws. All right. So the first fundamental of physics is mechanics, and that's going to be something like motion or energy conservation. That looks a little bit like this. You got like motion, energy, but the big challenge here is going to be vectors and multiple dimensions. All right. And I did want to give a little bit of a solution on how we might be able to sort of deal with this. And actually, if we look over here, this is one of the key parts is we want to have proportional drawings where like you can kind of see like if they might not be proportional to each other, but within itself, like this may not be quite in proportion, but if we can get to better proportions, then what happens is your math becomes easier because what you could do is you could say, okay, let's say I have two vectors like this, and I want to sort of measure their size. Like, yeah, let's kind of be a little bit sketchy because this is how it would be on a piece of paper, right? And you kind of see if you were to put an equation to this, then you could say that, up is equal to down pretty confidently, or pretty close at least. If it wasn't really proportional, you might have some doubts about that, right? So if you drew it kind of like this, a little bit in a rush or in a hurry, and you just kind of drew it like that, and then maybe you did some other stuff over here on the side and came back to it later, and then you tried to set up an equation, well, then you might be tempted to be like, well, I don't know what the relationship is between up and down. I'm not exactly confident, so I'm going to try to like solve some equation or something that's going to be like, you might get stuck. Another situation was here I have a line, okay, a line, and here's maybe a connecting line like this, right? So give them two endpoints or whatever. The idea is that if this line, if you look at it, it looks straight, so you might think that, okay, let's just call this a straight line. But really, there's two segments here, and there's an angle between them. So this is the issue with not having really, really good drawings and essentially drawing sloppily. So when you have proportional drawings and everything's really, really clear, uh, and it looks nice, and I try to do something like that here, where I try to really just kind of draw things well, then your math becomes easier. In fact, better drawings uh, equals easy math. So that's pretty cool. All right, and yeah, so vectors in multiple dimensions are kind of a hard part of regular old mechanics. But what about the electromagnetism? That's the second fundamental of physics. We look at waves and Maxwell equations. Mm, So that's kind of what that looks like. Here's some electrons and stuff, waves. Now the problem is that it's going to be difficult because you might encounter interference and differential equations, and it's a little bit weird to try to deal with those things. Oh, I got a little comment here. Hey, what's up, my man? Thanks for watching. And I'm trying this out. We'll see how this goes. Now let's see if we can solve the issue of interference and differential equations. Because one trick that we can do for electromagnetism, and this is for mechanics, right? But for electromagnetism, I think the best thing is to work on integration speed. And so there's one trick that we should all be familiar with. I'll try to do like a simple integral. Let's say we were doing something like the integral of, just do the integral of x, right? So that way we can all kind of do it and start from scratch. So if we integrate this, you know, usually you'd be like, okay, well, we know that it's going to be x squared over 2. should be the integral. You might want to add a plus c or something if you really want to, but that doesn't really matter too much. Um, but we've skipped a step, and I wonder if you know what we skipped, because there's actually it shouldn't be just 2 down here. There should be a 2 times a 1 down here. Well, that's weird. Where did that 1 come from? Okay, well, let's think about if we were to integrate of sine of 2x. Actually, I like doing the derivative as well because we all know how to do the derivative. We'll come back to all of this stuff in a second. Sine of 2x. We're taking the derivative of sine of 2x. If we were to take the derivative of sine of 2x, that's just going to be, I think it's negative cosine, might be positive cosine. Can't really read too well. Maybe it's just positive cosine. But we're going to do cosine 2x, and then you're supposed to multiply by the derivative of what's in there, right? 2. Okay, so that's interesting. This is the chain rule, right? This is the chain rule. And I know that we're integrating really slow right now, but what I'm going to try to do is we are going to cut through the u sub. So no u sub. If we ever try to do a u sub, we really got to stop and think, is this really necessary? Because most of the time you could just skip a u sub entirely and just get the answer. Just kind of like you know the answer to the derivative here. If you were to try to do an integral here, you might be tempted to like say u equals 2x and start doing a whole u sub. But that's not necessary because all we have to do is just realize, okay, what was the integral? I think at this point we say it's negative cosine of 2x. And then what we can do is instead of multiplying by the derivative, all we do is divide by the derivative. Okay, and so now we can see how there's a magical step that we have to do every single time we integrate, is that we actually have to divide by the derivative of what is in here, which is called the argument. Okay? Okay, so if we look at this integral, what we had to do is actually, rather than just say multiply by 1 down here, we really had to do for this integral. Let's forget about this plus c here, is we had to divide by the derivative of x, which is 1. We usually skip this step. All right, and usually we don't have to because here, like the derivative is 1, so there's no need for a u sub. But here, if you weren't really aware, and you might be tempted to use a u sub, all you have to do is just divide by the derivative of the argument. And so this can be applied to really, really, really complex integrals. All right, so let's say if it was something really crazy, like I'll make it something like x squared uh, uh, e to the e to the x to the third. Um, I don't know. Let's see if something like that works. Because like at this point, you might be thinking, "Oh, yeah, this is like really hard to use like the DI method. I don't know how are we gonna solve this." But there's a reason why I put x squared over here. The reason I put x squared right here is because the derivative of this is 3x squared. And so what happens is if I do an integral here, I know that forget about this, just like ignore that for a second and just focus on this piece. It's really important. This is kind of like this little guy is really what's integrating, and this little thing here is kind of like a flag on the side that's waving, a little waving a flag or something. But this thing is going to be integrated. So we know the integral of e to the x is just e to the x, so we're just going to go e to the x to the third. Um, And then what we have to do is bring this over with us, so we'll keep the x squared. And then we have to divide this by this little thing, so 3x squared. And because we divided by 3x squared, these cancel, and now you're just done with your integral. So it's 1/3 ex to the third. And so that's pretty cool. There's no need for u subs. You don't have to do any like variable switching or anything like that. You don't have to set up DI methods. All you got to do is just follow the chain rule for integrals. So in fact, this is called the chain rule for integrals. and it's kind of not really spoken of. But yeah, so you know, this is kind of the little secret that I learned one day from this other YouTuber. So that's pretty cool. I think his name was can't really remember. Dr. Payon? Yeah, I think that was what his name was. So that was pretty cool. You get to do the chain rule for integrals and basically instantly solve half the integrals that you solve. Generally, you require U subs, but one step, a single step will solve your integral just by dividing by the derivative of the argument, and you integrate this little piece, and you're done. So this should happen pretty fast, and integration speed should increase. All right, so let's take a look at the next topic. This was electromagnetism, covered mechanics. What about thermodynamics? So this is gonna have to deal with like statistics and entropy, which is some really like complicated topics. But if we go back to this little sheet right here, it's basically going to be like melting stuff, like phase transitions, heat transfer, systems, and thermodynamics in terms of like statistics, like microstates and entropy and counting those kinds of things. So it gets a little bit weird here. This is like really cool stuff. Like the math gets so strange. And the best way to understand thermodynamics is to think about playing Yahtzee. All right, so this is a little bit crazy, but let's think about Yahtzee because we have like a couple of dice. And let's say you're shaking the dice. Here's the dice inside of the box, inside of the cup, and you're kind of shaking it or whatever. And this is sort of randomness, and we could say it's also a lot of movement. uh, but not just that, also open possibilities because things haven't been selected yet. But as soon as you start rolling and landing some of these dice, like here's one die that's suddenly landed. We'll just call it a flip. So we'll just say like it's a thing there, and it landed. Now all of a sudden the temperature has decreased. Uh, so here, if there's more motion, the temperature is actually increasing here. And if we start to land these dice, all of a sudden the temperature decreases. So you're landing dice. I don't know what number it's going to show up here, but I'm just going to say that these are all ones because like quantum states is ones or whatever. So we're landing these dice and the temperature is dropping. And that is kind of how uh, thermodynamics and statistics kind of works, is because as you start to put dice back into here, sort of this kind of increases the temperature, increases the entropy, increases the available microstates. Because here the available microstates go up because you're shaking it all up, and here the available microstates sort of go down. I'll just put an arrow on this side. See, on this side it goes up, and on this side it will go down. And so, yeah, it's like kind of just rolling dice in Yahtzee. This is very strange, but this is exactly how thermodynamics and statistics works, and changing phases. Like it's these little molecules of ice, the molecules of water are basically getting shaken up and sort of split apart over here because the random movements is causing enough energy to break apart those bonds in the water, opening up the available microstates, causing more entropy in the system. I don't know. So basically, all this stuff is kind of happening in between, and the mathematics behind this is trying to explain it. So that's a little bit of thermodynamics, kind of crazy. Uh, yeah, and that's kind of basically the difficulty of thermodynamics is the microstates and the phases that we have. So understanding all that stuff that we just talked about is kind of what it looks like. You can see all these tiny little microstates getting shaken up, and then little wave functions here and there. So Well, I think that's the next topic. We're taking a look at quantum physics now. So particles and forces is what quantum physics is all about. And so I wanted to show that quantum physics is a lot like playing pool. So yeah, this is thermodynamics right here. Just a little recap. Remember that the mechanics over here was kind of like engines, wheels, how stuff moves. Um, this electromagnetism was really just about light. You gotta get the integration there. Yahtzee was about thermodynamics and how things change. And now we have a pool, and this is for quantum physics. It's kind of like a pool table. Not only that, but a magic 8 ball. Alright, this is why physics is so cool, guys. I don't understand. Everybody thinks it's really hard, but it's actually just like playing games. Literally, it's like playing Yahtzee, it's like playing pool, and like that little magic 8 ball thing. I'll explain why. So, like, yeah, I kind of need my little pool table over here. You can kind of see how, actually, I need both of these things. You can kind of see, uh, you got particles on a pool table, like, just intuitively. You can just sort of visualize if a particle is like going this direction and hits two particles or hits another particle or whatever, it's going to collide. And in fact, there will be two particles at that point of collision, and one will go this way, one will go that way. And then you can kind of draw this out. Remember the proportions I was talking about at this point? Really important to do this proportionally so you can see exactly how, if you go in with, you have to notice that we have two arrows here and we have a single bit here, but we're going to have to double that. Why? Because there's two arrows, so we kind of need one from the left plus one from the right. And this length here should be equal to this length here. So then we can see how, the momentum going in is equal to the momentum going out. This is one way we can solve this, a little bit of sort of quantum physics, but we would do this with more like, this is more like classical mechanics, but then you can also do this with like the Compton scattering stuff. So just like treating particles as like an electron, and it goes and hits um, a photon. Either this way or the other way. I can't remember exactly. Maybe the photon goes and hits the electron, and then some scattering happens. It looks something like that. But this is interesting. It's kind of like a pool table happening there. And if you really want to go to the really high levels of quantum physics where you have waves everywhere, all you got to do is just add wiggles into your pool table, add curvature into the pool table, and you'll think about how the balls are going to curve around on the pool table and the hell. And the thing is, that's when stuff moves around, right? Because there's sort of the quantum, uh, there's the wave particle duality, so you kind of have particles here. And then what about the waves over here? The waves are kind of like these magic 8 balls because you got this like sort of statistical distribution of like what could be, right? All the probabilities. And then over here, it's kind of like the highest chance of something happening. But whenever you choose something, say you choose a little point right here, it doesn't really matter. It's kind of like saying, wait a minute, you got a tiny little magic 8 ball that's at that little point right here, right? This is x, negative x. And then and this is just if that thing's there. Well, wait a minute. That's where the particle is. You just have you have the yes right there. It's the magic 8 ball that pops up. It's kind of like over here. These are little magic 8 balls. These are the little yeses, or the no's, or whatever it is. It doesn't matter what it is. The state. Uh, there's usually 6 states. If it was a block sphere, then you'd have 6 different states that you can land in. But um, yeah, this is kind of cool. Like, we're just basically shaking up the magic 8 ball, and then one of those options, one of those choices, uh, you might have 6 choices, right? And only one choice appears. And that's the window that you see that sort of gets pushed along this sort of timeline. Because think about now, the timeline is that there's now this, imagine a timeline here, and there's like a window that you get to see. And on that window, there's like pressed against it, there's the magic 8 ball that's showing you. And then if you want to wipe the window and reset that, then you have to kind of shake it all up again. And then you can try to take another roll and then see if you get another yes or a no here on the surface. This is some crazy stuff, man. This is quantum physics. And yeah, the math gets a little crazy. But these are the tricks to understand uh, intuitively what's really happening. All right, so now let's go ahead and oh yeah, so the problem with quantum physics is there's a lot of mathematical symbols. You might get like W bosons, Y for the photons, electrons, Higgs, crazy stuff is popping out of the thin air. It's a little bit weird. But anyway, let's head over to general relativity now. It's kind of the last topic of fundamentals. It's kind of more like astrophysics and gravity. And well, it's a little difficult because there's singularities and unknowns, stuff that's like really hard mathematically, and it's just so far out in space. It's really hard for us to sort of test it. So we don't know really what's out there. So I wanted to give a little trick on how we can sort of deal with that issue. And it's going to help with all the other stuff too. You might have noticed something I've been doing this whole time. Um, well, maybe I haven't been really doing it this whole time. But what's a really good idea is to color code stuff. I haven't really been doing it here because it's not incredibly complicated. But once things get really hard, especially like in mechanics when I was going back there and I was thinking, okay, like if there's a force here and then a force here, if I color code them like that, then I know that this one is specifically the normal force. And then when I solve problems over here in my equations, I'll use that. And this might be gravity. I guess we'll call it FG. Um, or we can even just say capital G just for fun, just to make it a little bit easier. But now I kind of have these idea of these two forces. What what, like if I make an equation now, instead of just saying up and down, I can now say that in this case it looks like n is actually less than g, even though it's not really supposed to be. And that's why having proportional drawings is actually better, because over here you can see how we have n and g, and in this case it's a little bit more obvious that n equals g. And well, I know we're going back to mechanics, but this is gravity. So this is kind of like level one general relativity in a sense. Thinking about the gravitational force there. So, when I was trying to figure out general relativity equations, I was essentially trying to color code all the uh, all the info. So I'm not really going to, go through all the equations of general relativity here, but the general idea of color coding will really help to just boost understanding quickly. Um, like here, what I can do is I can color the argument green. This is essentially what we want to be differentiating when we're oh my gosh, it's a little bit hard to do that. When we're trying to do these integrals, we have to actually differentiate the argument at the end. So you might as well just you know, it's right there. You have to know which one is the argument, and so you can pull it out. Um, you can do all sorts of crazy things. You can even color code the integral bars if you want to, like open and close the integral right here. with the color purple. And then all of a sudden you start noticing, hey, I missed the integrals, or I missed the dx right here, right? Let's check the dx. Okay, now you can color code it and you see mistakes popping out quite easily when you start color coding things. Here we actually had the dx. And you can see the use of color coding is just pretty awesome. Let's follow x to the third all the way down to see how it sticks around. Right. And argument got integrated here. And the last, oh yeah, I was going to come back to this, right? One, you could also just say that dx over dx. You see, because really what we're differentiating is x here. It makes it a little bit better. So we're differentiating x. It's the same thing as saying 1. But that's what happens after we do an integral. We have to divide by the differential of the argument. Awesome. Just like we did it with the chain rule, we had to multiply. Go ahead and use a red dot to show that here we use the chain rule as the red dot. And you can see how easy it is to understand when you color code stuff. This can apply to these simple concepts and you can apply to the harder stuff. This is the chain rule for integrals. It's literally the opposite chain rule of the derivative. Pretty interesting. And color coding is a lot of fun. It helps make the math more interesting. Awesome. Here it is right here, the chain rule for integrals. Boom. And that has been a color-coded setup. And this is how you can sort of extend this up to the mass of general relativity and do all sorts of differential geometries and all sorts of crazy stuff. It doesn't become too difficult when you use color coding techniques. So let's recap. We have the fundamentals of physics, and there's these 5 concepts. We got mechanics, electromagnetism, thermodynamics, quantum physics, general relativity, and there are specific challenges associated with them. I gave some good ways to sort of fix that. So proportional drawings are key. The integration speed using the chain rule for integrals. The Yahtzee method of sort of rolling dice and understanding temperature changing there. The magic 8 ball and pool table, things rolling around, bouncing around, and selecting quantum states. And we have just color coding to be able to just cut through the math and understand stuff really much clearer. It's going to help with the advanced stuff. All right, so these are the challenges for the fundamentals of physics. And this might be usually what's taught in a standard physics course. And there could be ways to do it without calculus, just with basic math. With calculus, you could use linear algebra, or you could start using differential geometry, depending on sort of what level you're interested in. And so basically this is how we start to unlock the archives of physical sciences to study these topics and get all into it and stuff. So I got this special physics formula sheet that's going to cover sort of the mechanical physics formulas. It's a free download. It's got a complete guide. It's going to save time. It's a little efficient review. And there's even a little nuclear physics chapter, also a quantum physics um, course upgrade, and even a study pack. There's all sorts of upgrades that you can get with this free physics sheet. Go ahead and check it out, physicsformulasheet.com, and that is a free download. I'll see you around. Thank you so much.